Okay, so welcome to this video, which goes with the workbook on counting techniques, and let's dive straight in. Right, so the first question says, if I have 3 hats, green, brown, and white, and 2 jackets, blue and green, how many combinations can I have if I must wear both items? Right, now, basically, if we really weren't too sure, we could sort of we could write them down. Okay, so let's go with hat and jacket. And so one option would be to go with a green hat and a blue jacket. But I could go with a green hat and a green jacket. I could also go with a brown hat and a blue jacket. I could go with a brown hat, so this is hats and then jackets, and a green jacket. Or lastly, I could go with a white hat and a blue jacket, or a white hat and a green jacket. Now, if you try and write them all down, that's as many as there are. And in fact, there are 6. Right. Next question. If there are 2 roads joining A and B, and there are 3 roads joining B and C, how many different ways can we get from A to C? Well, let's write them down. Okay, I could go on road number 1 and then road number 3. I could go on road number 1 and then on road number 4. I could go on road number 1, then on road number 5. I could go on road number 2, then number 3, road number 2, then number 4, and then road number 2, and then road number 5. And there are no more. So there's actually, once again, there are 6. Right. Now, what I'm hoping you might have noticed is that, in fact, this is just a multiplication of choices. So here there were 3 choices, and here there were 2 choices, and the answer is just 3 times 2. Here there's 2 choices of road that I can get from A to B, multiplied by 3 choices of road that I can get from B to C. Right, let's look at this one. This is now 3 items of clothing. All right, I've 2 shirts, 3 pairs of longs, and 4 hats. How many different outfits can I wear if I wear all 3 items? Well, not too bad at all, because it is just going to be 2 times 3 times 4. Right, and if you're not convinced of that, you need to pause the video and write them all down, and you'll see that it is in fact definitely not 12, but in fact 24. A way of maybe thinking about it is that if I didn't have the change of shirts, I just had longs and hats, the answer would be clearly 3 times 4, it would be 12. And now with each of those 12 outfits, if I introduce the 2 shirts, I've got I can double up, because I can either have the one shirt or the other shirt, and that's why that would then multiply by 2 to give us 24. Right, here's a little crossword clue, just a little fun thing, okay? A something in the attic can be considered a nuisance. Well, I can think of 3 things there. Maybe a cat, maybe a bat, or maybe a rat. Okay, it's got to be something AT, so those are the only 3 I can come up with. And then, a something is considered a good score in a certain sport. Well, in gymnastics, a 10 is a perfect score, all right? And in cricket, a ton is another word for 100. So I've got sort of 2 options that I can think of there, all right? And so, in fact, the total number of ways you can complete this crossword is going to be a choice of 3 times a choice of 2. It's actually going to be 6, all right? Cat with 10, bat with 10, rat with 10, cat with ton, bat with ton, rat with ton. Okay, and so we introduced this idea of the fundamental counting principle, and what it says is we multiply numbers of ways. We don't add them, we multiply them. So for example, if one thing can happen in m ways and another in n ways, then together they can happen in m times n, mn ways. Okay, let's turn over and see what's next. If there are 3 starters at a restaurant, 2 main meals, and 2 puddings, how many meals can I have? Right, assume that we eat them in standard order and we eat all 3 courses. Well, we've got a choice of 3 here, we've got a choice of 2 here, and we've got a choice of 2 here. Right, so the answer to that first question will just be 3 times 2 times 2, or 12. And again, if you're not convinced, write them all down. For example, soup, then chicken, then ice cream. Or soup, then chicken, then jelly. Right, I promise you there will be 12. Now the question asks, what if we only had 2 courses, but we still ate them in standard order? Now we've actually got to, and this quite often happens, we've got to actually sort of think about this a little bit, because there are actually 3 possible sort of scenarios. If I have no starter, right, if I have no starter, then I've got a choice of 2 mains, and with each of those mains I could have 2 of the puddings. So in fact, if I have no starter, there are 4 possible meals, all right? And the word here is or, all right? I could have no main course. I could just have a starter and a pudding, all right? And so if the number of choices I've got for starter, it would be 3, and the number of choices for puddings, 2, and I'd get 6, all right? Or, and some people really wouldn't like this, but I could have no pudding, okay, no dessert. No pudding. Right, and if I have no pudding, then I've got a choice of 3 starters and 2 mains for a total of 6. Now, the word is or, and generally in probability and in counting techniques, when we've got or, we add. So the total number of meals, because these are different scenarios, would be 4 plus 6 plus 6. It would be a total of 16 possible meals. All right, when we are doing probability, this counting techniques actually helps us work out our sample space. Let's look at some examples. If I toss a die and a coin, how many different possible outcomes are there? Well, on the die, there are actually 6 things that can happen, and on the coin, there are 2 things that can happen. So the answer is actually 12, because we will multiply them. If you're not convinced, you can write them down, and I'll quickly do this. Our sample space would look like this. Heads with a 1, heads with a 2, heads with a 3, heads with a 4, heads with a 5, heads with a 6. And then obviously each of those can also happen with tails. Heads with a 6. And then we've got all of them again. Tails 1, tails with a 2, tails with a 3, tails with a 4, tails with a 5, tails with a 6. Let's just tidy it up by putting some semicolons in between them. And if we count them, we'll see that there are indeed 12. We normally put like squiggly brackets, which no one knows how to draw, on around our sample space. Okay, suppose I toss 2 dice. How many possible outcomes are there? Well, there's 6 outcomes on the first dice and 6 outcomes on the second dice. So they're actually 36. There are 36 things that can happen when you throw 2 dice. And I want to just, while we're here, make it clear that like a 2 and a 1 is actually different to a 1 and a 2. In other words, you can get a total of 3 in 2 ways. So there would be a 2 out of 36 chance of a total of 3, right? Because we need to count these separately. What's the probability of getting a total of at least 10? Now remember what at least means. It means 10 or more. Okay, so I could get a 4 with a 6. Or I could get a 6 with a 4. I can't get a 7, okay, but I could get a 5 and a 5. Okay, and that only happens in one way, all right? Or I could get a 5 and a 6. That would give me 11. Sorry, I'm actually making a bit of a mess of this. Sorry, 5 and a 6, a 6 and a 5. Okay, what I actually meant to write down on this one was in fact a 6 and a 4. Let me just fix that. I can just find an eraser here. Right, so this was actually meant to be a apple. Goodness gracious. Right, a 4 and a 6, a 6 and a 4, a 5 and a 5, a 6 and a 5. All right, a 5 and a 6, a 6 and a 5, and lastly a 6 and a 6. So in fact, there are 1, 2, 3, 4, 5, 6. All right, so the probability of at least 10 is 6 out of 36, which actually simplifies to 1 out of 6. Okay, suppose I toss a coin 7 times. How many different possible outcomes are there? Well, on the first throw, there's a choice of 2. On the second throw, there's a choice of 2. On the third throw, there's a choice of 2. On the fourth throw, there's a choice of 2. Fifth throw, choice of 2. Sixth throw, choice of 2. And seventh throw, choice of 2. Right, and 1, 2, 3, 4, 5, 6, 7. 2 to the 7 is the answer, which is 128. There are 128 different things that could happen. One of those things, just for example, might be heads, then tails, then tails, then heads, then tails, then tails, then tails. All right? Okay. That's 1 out of the 128. Now, what's the probability of getting tails on at least one of the 7th rows? And remember, there's a little trick here, because the probability of at least one is 1 minus the probability of none. Okay, so in other words, this would be 1 minus the probability of getting heads 7 times. Okay, and remember, so we're really reinforcing some probability here. Remember that when we have independent events, we can just multiply them, okay? So the probability of getting a head and a head and a head and a head is just going to be a half to the power of 7. All right, and so in fact we get 127 out of 128. Now, if we just stop and think briefly, if you toss a coin 7 times, the chances of getting tails on at least one of those 7 throws is likely to be very high, and in fact that's the answer there. Right? We are counting every single possible one of the combinations of the 128 outcomes in the sample space. We're counting all of them apart from one. And the one we're not counting is when we don't get any tails at all. So there are 128 things, and the only one we're counting, the only one we don't want to count is when we get heads on each throw. Okay, right. Here's some ideas that come from sports tournaments, right? So in the IPL, there are 8 teams, and this is maybe an old stat, because I think there might be more now, right? Each team plays one another twice, home and away. How many matches would there be altogether? Right. Well, I'm actually going to, let's just think about it. I'm kind of going to ignore that, all right? And I'm going to think about this as follows. All right. Each team, there are 8 of them, and each will then play 7 matches. All right. They don't play themselves. All right. So 8 times 7 will be 56, and that's in fact the answer for the home and away thing, right? Because when we consider a certain team, all right. For example, suppose we consider the Chennai Super Kings, all right. They will play maybe against the Rajasthan Royals, but when we're considering the Rajasthan Royals, they will play against the Chennai Super Kings, and that's why the home and away things work. Okay, right? And that would be our answer. Okay, the other way of thinking about it is in terms of a team's home games. All right, they would play 7 sides. The first side would play 7 matches. The next team would play 6 matches. The next team would play 5 matches. The next team would play 4 matches. The next team would play 3 matches. The next team would play 2 matches, and the next team would play 1 match. All right. This actually, if we add these up, 13, 18, 22, 25, 27, 28, that's 28 matches. All right. And then the reason we would double that, all right, is because of the home and away. All right, and we get the same answer in both ways. We get 56 matches in total. Notice if they only play each other once, home or away, then we would halve the number back to 28. All right, this next one's quite cool. So in a Grand Slam in tennis, there are 128 players in the first round. All right, and so what happens is in the first round there are 128 players. In the next round, there are 128 players. There would be 64 matches, all right? Because 128 players playing singles, 64 matches, all right? Half of those 128 would be knocked out. So in the next round, there would only be 32 matches for the 64 players. Then in the next round, we got 32 players, so it would only be 16 matches, and so on. All right. This is what we call the semi-finals. Okay, there's 2 players. There are 4 players left, so 2 matches, and now there are 2 players left and only 1 match, and that's the final. And we can add all of those up. And if we add all of those up, we get 127. But a much cooler way of thinking about this is that there are 128 players, right? And every time there's a match, a player gets eliminated. So each match eliminates a player from the tournament, knockout tournament. All right? And we need, in order to establish a winner, we need 127 players eliminated. And so we need 127 matches. And that's a much more kind of elegant thing that you can do in your head than adding them up like we did above. Okay, right. Now, let's do a bit of an exercise. And really the ideal thing here is to pause the video, try this yourself, then let it play and see how you went. Okay, right, so let's take a look. How many 3-digit numbers can I make using these 1, 2, 3, 4, 5 digits if digits can be repeated? Well, in the first place, I've got a choice of 5. In the second place, I've got a choice of 5. And in the third place, I've got a choice of 5. And remember, we multiply choices, so we get 5 cubed or 125. Now, if I can't repeat digits, in the first place, the first digit, I've got a choice of 5. But now I've used one of them, so now I only have a choice of 4. And in the third place, I only have a choice of 3. And this comes to 60. All right, not surprisingly, there are far fewer numbers that you can use if you're not allowed to repeat digits than if you are allowed to repeat digits. Okay, so now we're going to look at 5-digit numbers, which can be made using these digits. 1, 2, 3, 4, 5, 6, 7. All right, okay. And we're not allowed to repeat digits. How many will there be altogether? Now, what we've got to decide, and the question would need to be clear, I don't think you can have a 5-digit number that looks like this. Right? So in other words, we're not going to allow a 0 in the first place. The question would have to make that clear. But let's assume that we're not allowing a 0 in the first place. Then how many are there if we're not allowed to repeat digits? Well, for the first digit, we've got a choice. There are 1, 2, 3, 4, 5, 6, 7 digits. We've actually got a choice of 6 for our first digit. Remember, we're trying to make a 5-digit number, 4, 5. Okay, and the reason it's a choice of 6 is because I may not use 0. Now, in the second choice, in the second digit, I'm actually going to have 6 choices again, because now 0 is available as a choice. Now, so far I've used 2 digits, so I've actually only got a choice of 5 left, and now I've used 3, so I've got a choice of 4 left, and then 3. And that would be my answer here. All right, this is actually 36 times 4 is 144. Oh goodness, maybe I'm not going to do it like that. I'm going to do 36 times 20, all right, which is 720 times 3. I think we get 2,160, and I hope I'm right. Okay, what's the probability that one of these numbers selected at random is an odd number? Okay, now, what we need to think about now is what digits must it end in order to be an odd number? And the only options here are in fact 1 or 3. So what we're going to do now, we're going to count how many end in 1. Okay, so what we've got our 5-digit number. And I'm going to put a 1 here. I'm actually going to write it with a black pen. So this is not talking about choices. That's the number 1 that's fixed there. Now I'm going to write the choices here in blue. Now, for my first digit, I can't use 1 because it's already there. I can't use 0 because we agreed we're not going to allow a 0 at the front. So I've actually got a choice of 5. Now, for my second digit, I've actually I've got a choice of 5 again. And the reason I've got a choice of 5 again, I can now use any of the digits apart from 1 and the one that I used here. And then it's going to go to 4, and then it's going to go to 3. All right. And so this is 25, it's 100, it's actually 300. All right. So there are 300 that end in 1. For exactly the same logic, the number that end in 3 will actually also be 300. So in fact, the probability that it ends in 1 or 3 is 600. In other words, the probability of an odd will be 600 out of the total. Remember, the probability of an event is the number of ways the event can occur divided by the total number of things that can happen, the sample space. Okay, and that's our final answer for that one. Okay, let's have a look now. It says, consider the digits 2, 3, 4, and 5. How many numbers greater than 400 can be made using some or all of the digits, but we're not allowed to repeat digits? Okay, now we've got some choices here because we don't have to use all the digits. We actually can have some 3-digit numbers. And we can have some 4-digit ones. Okay, right. So the number of 3-digit ones we can have, sorry, let's do the 4-digit ones first, okay? The 4-digit ones will automatically be bigger than 400, so I don't need to worry about that. Okay, how many choices? I'm not allowed to repeat digits. How many choices have I got for my first digit? Well, 4, for my second digit, 3, for my third digit, 2, and for my final digit, 1. Okay, and so I get 24. Right, but if I have 3-digit numbers, I can have 3-digit numbers, but they can't start with 2 or 3, otherwise they won't be bigger than 400. So for my first digit, I've only got 2 choices. All right, I can start with 4 or 5. Now for my next digit, okay, I can use any of the remaining digits. So I've got a choice, in fact, of 3, there are 4 digits here and I've used 1, so I've got a choice of 3. And then for the next digit, I've now used 2, so I've only got a choice of 2. And then for the last digit, I've only got a choice of 1. All right, so in fact, here I get 2 times 3 is 6, times 2 is 12. I get 12. So of the 3-digit ones, only 12 of them, all right, will satisfy. There are more 3-digit ones, all right. In fact, there are actually also 24 3-digit ones, all right, but only 12 of them are bigger than 400, so 36, all right, in total. Okay, and then in how many ways can 3 boys finish a race? All right, assume that there are no ties. Well, in first place, we've got a choice of 3 boys. In second place, we've got a choice of 2 boys. And in the final place, we've got no choices, 1 boy left, all right? And this happens to be 6. Let's just write them down with those stereotypical Tom, Dick, and Harry, and just check that those are all the possible orders. Here, Tom has come first, Dick second, Harry third. We could have Tom coming first, then Harry, then Dick. We could have Harry coming first, then Dick, then Tom. We could have Harry coming first, then Tom, then Dick. And lastly, the one that we haven't had is we haven't had Dick coming first, then Tom, then Harry, or Dick, then Harry, then Tom. And if we count all of those up, we'll see indeed that there are 6. All right. In how many ways can I arrange 4 books on a shelf? Well, in the first place, I've got a choice of 4 books. For my next position, I've got a choice of 3 books. For my next position, I've only got a choice of 2 books. And for my last position, I've only got a choice of 1 book. Now, this happens all the time in probability, in counting techniques, where we kind of multiply down to 1. All right? And so this thing's got a name. We actually call it 4 with an exclamation mark. All right? It's not, in fact, 4. All right? It's what we call 4 factorial. And we will see that we've actually got a factorial button on our calculator. All right, there it is, 4, shift, there, that's all, 4 factorial. And 4 factorial is in fact 24. All right, and in fact, here's a little formula, which unfortunately we don't get given, but the number of ways we can arrange n different things is just going to be n factorial. So the number of ways that 3 boys could finish a race, 3 factorial. The number of ways we can arrange 4 books on a shelf, 4 factorial. Okay, we're going to stop, kind of that's sort of the end of like chapter 1 in a sense, and then we will carry on shortly. Right, sometimes we want to count the ways in which objects can be arranged where we're wanting to keep some of them together, all right? And so let's just have a look at how this works. In how many ways can I arrange 7 books on a shelf? So I've got a total of 7 books, but I want the 3 of them by Wilbur Smith to stay together. So there's a kind of conceptual trick here. And what we do is we put a rubber band around the 3 books by Wilbur Smith. Right. That means now if we just think about, if we just draw like a little picture here, we've got the Wilbur Smith book 1, the Wilbur Smith book 2, and the Wilbur Smith book 3. All right. Then we've got 4 other books. Book 4, book 5, book 6, book 7. Okay. So in fact, we've got a total of 5 books. Right. And those 5 books because we're considering this as a kind of a book, which is why I've used quotation marks around that book. All right. Those 5 books can be arranged in 5 factorial ways. But for each of those, the 3 books inside the rubber band, the 3 Wilbur Smith books, can themselves be mixed up. All right. And because there are 3 of them, they can be arranged in 3 factorial ways. So we need to take these 2 numbers and multiply them. 5 factorial times by 3 factorial. Because as I say, let's suppose the Wilbur Smith books were over here. All right. Just with those books in that particular sequence there, those Wilbur Smith books could actually go in 6 ways in that position, 6 being 3 factorial. Okay, right, so let's now look at some examples. 5 friends go to the movies together and they sit in 5 adjacent seats. What's the probability that Nsako and Finn sit next to one another? Well, the total number of ways they can sit would be 5 factorial. All right. Now, what we're going to do, we're going to put a rubber band around Nsako and Finn. Okay, and then there are 3 other friends. Okay, so this person, let's just draw them here. They are different, these 3 other people. All right. So we've actually got 4 people. Right, I'm counting Nsako and Finn as a person. So 4 people can be arranged in 4 factorial ways. But for each of those, we need to multiply by 2 factorial. 2 factorial happens just to be 2, and that's because Nsako and Finn can switch around. Okay, and so now that's the number of ways where Nsako and Finn are together. All right, so the probability that they're together, remember, is just the number of ways that they are together divided by the total number of ways. So it's going to be 4 factorial, 2 factorial over 5 factorial. Right. And that actually works out to 2/5 or 40%. Yeah, I hope I've got that right, but I think I have. Okay, right. Now, what's the probability that Tapiwa and Michael do not sit next to one another? Well, we've just changed the names here, but basically, the probability that they do sit next to one another, if we did the calculation, would be 40%. So the answer to this would just be 60%, because they are either next to one another or they're not. So we just use the idea of a complement. Right. In my cupboard, I have 5 long-sleeved shirts and 3 short-sleeved shirts. Now, I hang them randomly. What's the probability that the long-sleeved shirts end up next to one another? So what I'm going to do is I'm going to put the long-sleeved shirts into a rubber band. 5 of them. Right, and then I've got 3 short-sleeved shirts. Right, so I've actually got 4 shirts altogether. So 4 factorial, but I need to multiply by 5 factorial for the kind of orderings inside there. All right, and then I need to divide by the total, and the total sample space is just 8 different shirts, which can be arranged in 8 factorial ways. Okay, I'm not going to work these out. The short sleeve shirts end up next to one another. Well, this time what I'm going to do is I'm going to put a rubber band around the short sleeves. Okay, and I'm not going to have a rubber band around the long sleeves. So I could have, for example, long sleeve 1 over here, long sleeve 3 over here, long sleeve 5 over here, long sleeve 2 over here, and long sleeve 4 over here. All right. So there actually are 6 shirts here, and they can be arranged in 6 factorial multiplied by 3 factorial for the 3 inside the rubber band over the sample space of 8 factorial. Okay, and then what about both the long sleeved and the short sleeves next to one another? Well, now I actually need 2 rubber bands. All right, so I'm going to have my long sleeve shirts over here. Okay, notice they can be in any order inside the rubber band. Long 1, long 3, long 4, long 2, long 5. Okay, and then next door I'm going to have my short sleeves in a rubber band, maybe short sleeve 3, then short sleeve 1, then short sleeve 2. All right, so I've actually kind of got 2 shirts. Now 2 shirts can be arranged in 2 factorial orders. All right, in other words, either the long sleeve then the short sleeve, or the short sleeve then the long sleeve. But I need to multiply by 3 factorial for the short sleeve swapping around inside the rubber band, and by 5 factorial for the long sleeve swapping around inside their rubber band, and then I must divide by the sample space, which is if there was no rubber band and there were no restrictions. Okay, I haven't worked these out. These are all fractions. They're all between 0 and 1, as all probabilities need to be. Okay, suppose I hang my shirts, 8 shirts randomly in the cupboard. What's the probability that the 3 green ones end up next to one another? So I've got 3 different shirts, but they're all green. Okay, once again, rubber band around them. Green 1, green 3 maybe, green 2. And then I've got my other shirts, and there will be 5 others. Okay, sorry, no rubber band. So maybe shirt 5, maybe shirt 3, maybe shirt 1 and 4 and 2 are on this side. All right, so the probability that the greens are together, okay, the number of ways for the greens together, I've actually got 5, I've actually got 6 shirts times 3 factorial for the ones moving around inside the rubber band over the total of 8 factorial. Okay, we work all of that out. Okay, these things are surprisingly easy to work out in your head, actually, because 8 factorial is 8 times 7, and then from 6 down to 1. 8 factorial is actually 8 times 7 times 6 factorial. So the 6 factorials will cancel. So I'll get 8 times 7 left on the bottom, and I've got 3 factorial on the top. So it's actually 6 out of 56, right? Which can simplify further. It's 3 out of 28. Okay, right. I'm going to stop this little video just there. Okay, so next up we're going to look at arranging things where some of them are identical. Okay, so now suppose we had 5 beads. All right, 3 are red, completely identical, and then there's a blue one and a green one. Now, if they were all different, okay, then they would be able to be arranged in 5 factorial ways. Okay, so what I've suggested here is that we draw a tiny little 1, 2, and 3 on each red bead, so that if you kind of zoomed right in, you would be able to see those little numbers on the beads. Right, then they'd be arranged in 5 factorial ways. All right, but for any one of those, so that's actually 120. So for any one of those 120 ways, right, 6 of them would actually look identical, right? And the reason it's 6 is because, so what I've got here, I've got all the 6, okay? We've just swapped the red ones, which remember have got microscopic little numbers on. We've just swapped them around, okay? And the 3 red ones can go in 3 factorial ways, right? So if your eyes aren't that great, these are all going to look the same. And we mustn't actually count these differently because the red ones are actually identical. Right, so what we need to do is we need to take our 5 factorial and we need to divide it by 3 factorial for the number of ways the number of ways the 3 identical beads can be arranged. Okay, right, so that's that, okay. Now, how many different arrangements can I make with the letters tutor? It's actually kind of almost exactly the same question. If all the letters were different, it would be 5 factorial. But I need to divide by 2 factorial, right, for the repeated t's. Okay, this is actually 60. And this was 120 divided by 6. This is actually 20 in the end. It's the actual final answer. Right. In how many ways can I arrange 5 beads in a row if 2 of them are identical? That's actually an identical question to the one above. Okay, it's just the same as the letters, but they are beads. In how many ways can I arrange 5 beads in a row if 3 of them are identical? Well, that's actually the same as the first question, 3 factorial. How many words can I make using the letters? Senseless. Okay, now what happens here is that there are 5, actually a total of 9 letters, all right? So if they were all different, they would be able to be arranged in 9 factorial ways. But I need to divide by 4 factorial for the e's, which can swap around, and by 3 factorial for the, 4 factorial for the s's, which can swap around, the 4 s's, and 3 factorial for the e's. Right, and so that's the number of words I can make. Okay, yeah, there's an L and an N, and so I always sort of do a little bit of a cross check here. So there's a total of 7 on the bottom, which are kind of ones that are repeated, out of 9, and there's 1 L and 1 N, so it's all good. Okay, right, and so here's a formula. You don't get given this formula, but if you've got N objects, and A of them are identical, B are identical, and C are identical, then the number of ways you can arrange them is N factorial over A factorial, B factorial, C factorial. Okay, so let's have a look at this. How many different words can be made with the letters mathematical? Okay, now, so the number of ways we can do that is we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 letters altogether. All right, so 12 factorial, if they were all different, I need to divide by 2 factorial for the 2 m's. There's a total of 3 a's. I need to divide by 3 factorial. There is a total of 2 t's. All right, I think that's right. There's only 1 e, there's 1 I, there's 1 c, there's 1 l, and there's 1 h. Yeah, so 2, 5, 7, yeah, that's it. Now, what's the probability? So this is the sample space, okay? This is the total. What's the probability that the 2 n's end up next to one another? Right, so what I'm going to do, okay, because they're identical, I don't need to count, I don't need to multiply by 2 factorial here. I'm just going to put the 2 m's into a rubber band, all right? So now, the number of ways I can have the 2 m's next to one another, basically I've got 11 letters, all right? And that would be divided by, all right, because I'm counting this as one letter, I would need to divide by 2 factorial for the repeated t's and 3 factorial for the repeated a's. Okay, so this is the number of ways where the m's are together. Now that's not the answer to the question, because the question asks for a probability. So the probability that the m's are together right will be this number divided by all over, right, this number. The reason I'm writing it like this is because I'm now going to calculate this, hopefully without a calculator even, believe it or not. 2 factorial, 3 factorial, 2 factorial, right? Because remember, when we divide fractions, we're going to kind of tip in time. So this is going to be 11 factorial, 2 factorial, 3 factorial, multiplied by the 12 factorial will now go to the bottom. And on the top, I'll get a 2 factorial, a 3 factorial, and a 2 factorial. Okay, and remember what I can do is I can divide out anything that's equal. So let's divide out a 2 factorial and a 2 factorial, a 3 factorial and a 3 factorial. Remember, an 11 factorial and a 12 factorial. 12 factorial is just 12 multiplied by all the numbers below it. In other words, multiplied by 11 factorial. Right, so in fact, the 11 factorials will cancel, just leaving a 12 on the bottom. Right, and on the top I've got a 2, so the final answer is 1 over 6. Okay. Now, this is slightly more interesting. The word starts and ends with the same letter. Now, we've got to count different cases differently here, okay? It obviously can't start and end with L, because there's only one L. But the options are, it could start and end with M, all right? Now, if it starts and ends with M, then the M's are out of it. They're kind of on either end, right? Now, I've got 10 letters left, so 10 factorial, but I'd have to divide by 2 factorial for the repeated A's, 2 factorial for the repeated T's, and 3 factorial for the repeated a's. That's how many words I can make if I sort of take the m's out and I put them first and last. All right? But I can actually get exactly the same number if I take the t's out. Okay, so that's kind of starting and ending with m. If I start and end with t, I actually get exactly the same, because I can have, there'll be 10 letters, 10 factorial, but I've still got to remember I've got 2 possible m's now inside, and I've still got my 3 a's. All right. Now, just be careful, because when we do, you might be thinking, well, these are all going to be the same. The only other possibility is that thing starts and ends with an A, all right? But now this will be 10 factorial, all right, because I've taken the A's out. But it will actually be 2 factorial for the 2 M's and 2 factorial for the 2 T's. Right. Now, these are numbers of ways. So the probability is actually going to be this plus this plus this all over the sample space. All right. So it's going to be 10 I'm just going to write it down. It's going to be 10 factorial over 2 factorial, 3 factorial. And now that actually happens twice, so we could actually just, to save ourselves a little bit of effort, we could multiply that by 2, add this one, all right, all over the sample space. And remember, the sample space is 12 factorial over 2 factorial, 3 factorial, 2 factorial. Okay. Now, that comes to something. I don't know what it comes to, but suppose it, I'm just going to make up a number, okay, and it definitely will be wrong. Okay, suppose this came to, say, 20%, all right? That means that there's a 20% chance that the word starts and ends with the same letter. And that must mean that there's an 80% chance that it doesn't start and end with the same letter. Okay, so notice we've used the complement again. Okay, right, now I'm going to stop the video here, and then in the last video we'll look at these past paper questions. Okay, so that sort of concludes all the sort of teaching. Now let's do some practice. All right, so let's look at this question. Steve needs to set up a format for passwords. Okay, he's decided on having letters, 26 letters, followed by digits 0 to 9, and both can be repeated. Calculate the number of passwords that can be created using 2 letters followed by 2 digits. Okay, so basically in terms of choices, all right, he's going to have 2 letters. There'll be a choice of 26. All right, and then here there'll be for the first letter, because they can be repeated, there'll be another choice of 26. All right, and then he's got a choice of 10 digits, 0 to 9. And then 10 digits. So often they'll give like a sample code. For example, they might say you can have AA23 or something, okay, as an example. Okay, and that just conveys that we can repeat stuff. Okay, so now we just simply multiply these together. I think when you multiply 20 by 26, you get 576, and then there'll be 2 zeros on the end. So I'm thinking 57600, so 57,600. Okay. He thinks that he'll need to cater for 3 million different passwords. He's going to stick with 2 letters, but he'll need more digits. Okay, and determine the least number of digits he'll need. Well, you can do this kind of by trial and error, actually, but this piece here is there are 576 choices he gets with the letters, all right? And then we want times 10 to the n, all right? In other words, we want to know how many digits, because if for every digit we're going to multiply by 10. We want this to be equal to 3 million. All right, and this is just a little log equation. Okay, I think that's 3 million. Yeah. So what we're going to do is we're going to divide both sides by 576, and then we're going to find the log. So n will in fact be log base 10 of 3 million over 576. I can tell you very few people will do it like this. Most people will just do it by trial and error, and that would actually be fun. Right, let's just have a look at this. So we're going to find the log of 3 million over 576. All right, and we get 3,7. Right, so we actually will need n to be 4. All right, you'll need at least 4 digits. And we'll see that when he has 4 digits, right, we'll have 5, 7, 6, and then 4 zeros. 1, 2, 3, 4. All right, and that's actually 5.76 million. All right, but if we take a digit off, then we've actually only got 500,000. All right, and we need 3 million. So at least 4 digits. Right, then let's look at this one. A box contains cards numbered from 1 to 7. 2 cards are drawn at random without replacement. Find the probability that the numbers on the 2 cards drawn out of the box give an odd product. Okay, now the only way you get an odd product is to have one of them being odd and one of them being even. In other words, we need an odd, then an even. All right, or an odd, then an odd. This is not actually true what I said just now. All right. In fact, this one does not work at all. Odd then even gives you an even. All right, because obviously that's got a power of a multiple of 2 in. So actually, we need them both to be odd. All right. That's the only possibility. So if we draw a little tree diagram, okay, on the first draw, this is draw one. This is the first card. And then the second card. Right, we could get an even or an odd. First up. Now the cards are numbered from 1 to 7. All right, so if we just look at these numbers from 1 to 7, 1, 2, 3, 4, 5, 6, 7. There actually are 4 odd numbers in amongst those, and there are 3 evens. So the probability of getting an even up front is 3 out of 7. Okay, we actually don't really need to carry on with this branch, because here obviously we could get an even again or an odd again, but that won't actually help us, right? Because we actually need both of them to be odd. The probability of getting an odd, all right, is in fact 4 out of 7, first up. Then what we want is we want another odd. And the probability of another odd, now we've taken one odd out, so this will now be out, this will now be down to 3 out of 7. And remember, we multiply probabilities, so final answer is 12 out of 84. Not 12 out of 84, 12 out of 49, sorry. 7 times 7, 12 out of 49. That's the final answer to that question. Okay, let's look at the next one. A group of friends decide to plan a trip to Europe. All right, and they're going to visit these different places. 1, 2, 3, 4, 5, 6 different places. Okay, what's the total number of different orders that they could visit those 6 different places? Well, just 6 factorial. Then it says Rome, Madrid, and Florence are grouped together in that order. Okay, so what we've got now, in a way, we've got like a rubber band around Rome, Madrid, and Florence. Okay, and then we've got 2 other places, okay, which are Milan, sorry, 3 other places, Milan, Geneva, and Paris. All right, now the number of ways you can arrange this, all right, the number of ways they can arrange their visit now will just be 4 factorial. We're not going to multiply by 3 factorial because Rome, Madrid, and Florence are not swapping around in terms of orders. Okay, so that's our answer to number 2. Right, then it says, what's the probability that they will visit Rome, Madrid, and Florence one after the other in any order? All right, so now what we've got to do, we've got to work out how many arrangements are there if Rome, Madrid, and Florence are together but in any order. Now that would be 4 factorial times by 3 factorial, all right? But remember that the question is asking for a probability. So that would be out of 6 factorial. So that would be our answer for that question, right? Again, we can actually work this out quite easily in our heads, because this is actually 4 factorial. This is 3 factorial. Remember, 6 factorial is actually 6 times by 5 times by 4 down to 1. And 4 down to 1 we can write as 4 factorial. Now we can divide the top and the bottom by 4 factorial. All right, you can do this on a calculator as well. You do need to put the time signs in if you use a calculator. So we actually get 3 factorial, which is 6, over, and that 6 will in fact also divide out with that. All right, so in fact we get 1/5 as our final answer for that one. Okay, the next one, the word catalyst is given. Determine the number of different ways that the letters can be arranged. Well, there are 1, 2, 3, 4, 5, 6, 7, 8 letters. So 8 factorial. However, right, there are 2 A's. So I must divide by 2 factorial for the 2 A's. There are 2 T's. I think that's all. Okay, there's 2 A's, 2 T's. There's an L, a Y, an S. L, Y, S. And a C. Sorry, so that's correct. Okay, all right. Now, this next question, I remember it being asked. It actually caused quite a lot of kind of heartache. There's 6 red cards and a black card in a box. Busi and Kanya take turns to draw a card at random from the box, with Busi being the first one to draw. The first person who draws a black card wins the game. Assume that the game can go on indefinitely. If the cards are drawn with replacement, okay, so in other words, we put the card back in each time. Determine the probability that Kanya will win. Okay, now if we draw a tree diagram here, and this is kind of actually a sort of infinitely long tree diagram. So the first draw is Busi. Okay, now the card will either be black, all right, or it will be red. Okay, now if it's black, Busi wins, all right, and there's a 1/7 chance that Busi wins, all right. If it's red, then Kanya has a turn. And so what I'm going to do is I'm going to use a blue pen for sort of Kanya's turns, okay. So this is now Kanya. Just trying to remind myself how to spell Kanya. There we go, Kanya. All right. Kanya could get a black, all right, okay, or she could get a red. Now, if Kanya gets a black here, she's got a 1/7 chance she's got a 1/7 chance of getting the black here, all right. But she would need a Busi to have got a red, which has got a 6/7 chance. Okay. So this possibility for Kanya to win is in fact 6 out of 7 squared. All right, that she wins on her first draw. All right, now it's Busi's turn again. All right, now Busi could, I'm drawing Busi's in red. She could get a black, in which case she wins, so she's got a 1/7 chance of winning here. All right, but she could get, sorry, this chance of Kanya rather getting a red would be 6/7. All right, okay. The chance of Busi getting a black would also be a red would be 6/7. All right. Now it's Kanya's turn again, sorry. Okay. And she either gets a black, which has a 1/7 chance. All right. Or she gets a red, which has a 6/7 chance. Okay. Now, if we look at this probability of Kanya winning, okay, it's basically 6/7 times 6/7 times 6/7 times 1/7. Sorry, I'm actually just going to go, yeah, this, right, I'm going to just fix that. So her chance on the first throw, her chance of winning on the first draw would be 6. It would be 6/7 multiplied by 1/7. That's on the first throw. All right, her first draw rather. Okay. In order for her to win on her second turn, it would actually be 6/7 times 6/7 times 6/7 times 1/7. So it would be 6/7. All right, times 1/7. But the 6/7 would actually have to be cubed. all right? And then on her next turn, if we think about it, we actually, Boise would need to draw a red again, which would be another 6/7, and then Kanya would need to draw a black. So on the next one, it actually goes up to 6/7 to the power of 5 times 1/7. And this carries on forever. All right. Now, this is an infinite geometric series. That's the first term. Remember, the formula for the sum of an infinite series is a over 1 minus r. So it's a over 1 minus r. So it's actually going to be, a is 6 over 49. All right. R, what we're multiplying by to get from this term to this term is actually 6 squared over 7 squared. And then 6 squared over 7 squared again, 2, because the power is increasing by 2. All right. So it's actually 1 minus 36 over 49. Right. And if we type all that into a calculator, this is what we get. All right. So we get 6 over 49 over 1 minus 36 over 49. All right, and we get 6 out of 13. Okay, actually ends up getting to about 46%. Okay, 6 out of 13. Now, so Kanya's actually got only a 6 and 13 chance of winning, and obviously Boise must have the balance. Boise's got a 7 and 13 chance of winning, which isn't surprising because she starts. Okay, that question caused a lot of heartache when it was asked. Right, let's look at what's next. Consider the word circle. All right. If two letters are selected at random without replacement, determine the probability that both letters are C. Right. You can do this with a tree diagram, or you could just say, well, what's the probability that the first one is a C? It's 2 out of 6. All right. Now, the probability of the next one being a C, there's only 5 letters left, and only one of them is a C, so it would be 1 out of 5. All right. And we multiply those two, and we get a 15th. All right, what's the probability that only one letter is a C? Now, again, in a way, it's easier to draw a tree diagram. So I'm just going to sort of show you basically what the structure would be. We either get a C or we don't get a C. All right. Then on the next draw, we either get a C or we don't get a C. And here we get a C or we don't get it. So it's don't get a C, and here we get a C and don't get a C. Okay, so basically getting a C and then a non-C would be 2 over 6. That's to get the C. Multiplied by, now to get a non-C, all right, there are 4 out of 5 that are non-Cs. All right. But we could also get the non-C first, okay? And that would be 4 out of 6. And then we want a C, and obviously that would be the 5 letters left and 2 of them are C's. Right. As I said, if you put the probabilities onto the tree diagram, you can actually see why this is why it is. Okay, so it's actually 8/30ths plus another 8/30ths. It's actually 16/30ths. All right, determine the number of different 6-letter arrangements that can be made. Well, 6 factorial, and then we must divide by 2 factorial for the repeated C's. It actually comes to 360. All right. How many word arrangements can be made if the word it starts and ends with the same letter? Well, basically, the only letter it can start and end with is the C's. So what we're asking ourselves is how many ways can we arrange these 4 letters, I, R, L, and E? Okay. And the way we can arrange 4 different letters is just 4 factorial. So there are 24. Okay. Right. Then 10 coins are arranged in a row. 5 are 1 Rand coins, 3 are 2 Rand coins. Okay, and 2 are 5 Rand coins. How many different arrangements are possible knowing that all the coins of the same value are identical? Well, we've got a total of 10 coins. If they were all different, we could arrange them in 10 factorial ways. Right? This is just like the letters in circle above. But we need to divide by 5 factorial for the repeated 5 1 Rand coins, by 3 factorial for the repeated 2 Rand coins, and by 2 factorial for the repeated 5 Rand coins. Okay, right, then let's see what's next. Mr. Werter realized that he had forgotten his password to log into internet banking. Okay, and his password is made up of 5 letters. The first and last letters are the same, and the middle letters different to each other and different to the first and last. He has 3 attempts before being locked out of his account. How many passwords can he choose from? Right, well, so basically, they are letters, all right? So the first, goodness, okay, the first letter, okay, these two are going to be the same, all right? So he's got a choice of 26 letters to put in here. That will be exactly the same, so we don't have to worry about that, okay? Then he can choose, for here he can choose a choice of 25. For here he can choose a choice of 24. And for here he can choose a choice of 23. All right, so we multiply these choices, remember the fundamental counting principle? So that will be the answer to number 2. Okay, determine the probability that he'll unlock the account on the first attempt. Right, well, he is going to try one of all those numbers. So the answer to number 2 will just, his chances of unlocking on the first attempt are going to be 1 over 26 times 25 times 24 times 23, because he's going to try one of those. All right, and it's highly unlikely that it would be right. Okay, show mathematically that his chance of being locked out of his account on 3 attempts is almost 1. Right, okay. So now on the first attempt, all right, he tries one of these numbers, all right, and that's the probability of him unlocking the account, all right. Now, okay, so let's just think the probability that he gets locked out on the first go, all right? Remember, this is the total number of passwords. Is basically he tries. Sorry, the probability that he's wrong on the first one, okay, will be. I'm just going to get what the value of 26 times 25 times 24 times 23 is. 26 times 25 times 24 times 23. Right, 3588. 800 3588. 358800. Okay, right. So on the first, his probability of getting it wrong on the first time is actually 358,799 out of 358,800. Yeah, because that's the chance that he gets it wrong. All right. Then the chance that he gets it wrong on the second time, right? He won't try the wrong number again. So he's going to, this will go down by 1, 358,798 out of 358,800. And then on the third time, okay, that he gets it wrong a third time, he's obviously not going to try one of the 2 numbers that he's tried so far. So this will go down slightly. His chances are improving slightly as he goes, but he's only got three attempts. Okay. And so if we work that out, that's the chance that he gets it wrong 3 times in a row. Okay. And if we work that out, it's going to be, I can't be bothered to type that into a calculator, but it's going to be very, very close to 1. It won't be quite 1, but it'll be very, very close to 1, which is what the question asked us to show. Right. Consider the word Olympiad. All right. The word Olympiad. How many different six-letter words arrangements can be made if the letters may be repeated? All right. Well, we can. Okay, six-letter words. Okay, so there are actually 7 letters here in Olympiad. No, they're not. They're in fact 8 letters. All right. If we want to make a 6-letter word and we can repeat letters, then there's actually a choice of 8, a choice of 8, a choice of 8, a choice of 8, choice of 8. We need one more letter here. Choice of 8. So it's actually 8 to the power of 6. All right. How many 6-letter word arrangements can be made if the letters may not be repeated? Well, now for our first letter, we've got a choice of 8. For our second letter, we've only got a choice of 7. For our third, a choice of 6. For our fourth, a choice of 5. For our fifth, a choice of 4. And for our last, a choice of 3. Now, this is not quite 8 factorial, okay, but we would multiply those together. All right, it's actually going to be 8 times 7 times 6 times 5 times 4 times 3. All right, it's actually going to be 8 factorial divided by 2 because we're not multiplying in the 2. So let's just work it out like that. 8 factorial equals divide 2. 20,160. Right. A box contains 3 40-watt bulbs, 5 60-watt bulbs, and 7 100-watt bulbs. Right. 2 bulbs are taken out at random and at the same time from the box. Okay. What that means is that they're not replaced. Okay. Represent the above information on a tree diagram. Okay. It's not really clear what's kind of happening here, but basically our first bulb could be a 40 or a 60 or 100. Okay. The next bulb could be a 40, a 60, or a 100. Right, 40, 60, 100. Okay, the probability of a 40 is 3 out of, there's actually 15 bulbs altogether. All right, 3 15ths. The probability of a 60 is 5 15ths. And the probability of 100 is 7 15ths. Notice that these add up to 1. They have to add up to 1. Now, if we've taken out a 40, the probability of getting another 40, there'll only be 2 left out of 14 globes that are left. There's still 5 60s, and there's still 7 hundredths. Okay, so notice again, these add up to 1. If we took out a 60, then there's still 3 40s, so it would be 3 14ths. There are still, no, there's only 4 60s left, so it would now be 4 14ths. And there's still all 7 hundredths, so it would be 7 14ths. Notice that those add to 1. All right, and then lastly, if we took out a 100 first, then there's still 3 40s, so there'd be 3 14ths here, and then 5 14ths. All right, but there would only be 6 hundredths left, and there would be 6 14ths. And again, those add to 1. All right, okay, I'm not going to multiply them down the branch. Let's see what the next part of the question says. It says, calculate the probability that the sum of the watts of the bulbs taken out is 160. Now, the way we're going to get 160, right, is to actually get, we can't get 160 if we take out a 40 first. We can either take out a 60 followed by 100, so in other words, that branch, or we can take out 100 followed by 60, in other words, that branch. Now remember, the probabilities, we're going to multiply down the branches. This one is going to be 35, 5 times 7, 35 out of 15 over 14, 35 over 15 times 14. All right, I'm just going to work out what 15 times 14 is. Should be able to do that in my head, but not today. 210, all right, 35 out of 210. And in fact, this one is also going to be 35 out of 210. And so the probability of getting a total of that of 160 watts, we must add these two together, and we get 70 out of 210, which happens to be exactly a third. Okay, right. Let's have a look at the next question. Maria decides to enter two different maths Olympiads. The probability that she wins the first one is 2%, and the probability that she wins the second is 0.08%. Assuming that that winning the different Olympiads are independent, determine the probability that she'll win at least one of them. Okay, so again, we can do a tree diagram. So this is the first one, and she either wins or doesn't win. Okay, all right, and so the first one is there's a 0.02 chance of winning, and obviously a 98% chance that she doesn't win. The second one, right, there's an 8% chance, this is obviously an easier one, all right, there's an 8% chance that she wins, and obviously a 92% chance that she loses. Right, and here, so this is when I say loses, that means doesn't win. Does not win, wins, doesn't win. Okay, so this is going to, in fact, be 0.08. This is going to be 0.92. Right, and remember the probability of winning at least one. The only one that we don't want to count is where she doesn't win either. Right, so basically, if we work this, we could work out all these probabilities, but remember the probability of at least one, winning at least one, is 1 minus the probability of winning neither. Okay, and the probability of winning neither is going to be 0.08 times 0.92. Sorry, 0.98 times 0.92. Okay, let's just work that out. So 1 minus 0.98 times 0.92, and we get that. All right, and so it's about 0.0984 or 9.84%. So it's got 9.84% of winning at least one of them. Okay, all right, and if we turn over, 5 cards given below are used by players in the game to create 5-digit codes. All right, so no repetitions allowed. How many unique 5-digit codes can be created? Well, they're just 5 things here, and they can be arranged in 5 factorial. How many unique 5-digit codes starting with a number can be created? Now, if it starts with a number, there's only a choice of 3 for the first thing, right? Because there are only 3 numbers. Then for the next place, there's actually a choice of 4, all right? And the reason being is we can use any of the other 4 cards. And then for the next place, right, there will be a choice of 3. And then for the next place, there will be a choice of 2. And then for the last place, there will be a choice of 1. All right. So in fact, it will be this. It will actually be 3 times 24. It will be 72. Okay. Right. And that's what is the probability that the 2 letters will never be next to each other in the code? Okay, so the way I would do this is I would put a rubber band around them, okay, and I would put them next to one another, okay. Right, so they're the 2 letters. And the number of ways that you can make a code with the 2 letters together, right, there's 4 objects here. They can be arranged in 4 factorial times 2 factorial, and the reason being is that that's in there, out of the total. Okay, so the probability that the 2 letters are together is just that number over there. And that actually simplifies quite easily. That cancels just to give a fifth. So it's actually 2/5. All right. So the probability that the 2 letters are together is 2/5. And so the probability that the 2 letters are not together, the word never is actually not very helpful here, but that they're not together is 3/5. Okay, it's just the complement. Right. And I thought we were finished. Okay, you have 3 6-sided die that you use to create a geometric series by randomly throwing the die. The first one's red, the one's red, the one's blue, and the third is green. The number on the red dice represents the value of the first term. You then take the value on the blue dice and divide it by the value on the green dice to generate the common ratio. What is the... Yeah, I'm going to have to remind myself how this question works. Okay, so we've got red dice, blue dice, green dice. Okay, and there's 6 possible things that can happen on that dice, 6 on that dice, 6 on that thing, on that dice. So the sample space has actually got 6 cubed, which is 216 possibilities. What we got to do is work out how many of those possibilities are going to result in our geometric series having an infinite a sum to infinity of 10. Okay, now the number on the first dice represents the value of the first term in the series. Okay, so and then you take the value on the blue dice and divide it by the value on the green dice to generate the common ratio. Right, so what we're going to have to think about is how are we going to get values of 10 as an answer, remembering that our sum to infinity formula is a over 1 minus r. Okay, this actually requires quite a lot of sort of thought. Okay, if we had a being 5, all right, then obviously if we were to divide by a half, all right, then that would give us 10. All right, you can't, okay. You could also have a being 2 and dividing it by a fifth, all right? 2 divided by a fifth would give you 10. In other words, if your common ratio was 4/5, okay? I don't think you can get 10 any other way. No, you can't, all right? Because you'd have to divide 1 by a tenth, all right? And you can't get a common ratio of 9/10 from the dice. You can't divide 3 by anything to get 10, right? And you can't divide 4, maybe you can. You can divide 4 by 2/5. That would get you 10 as well, all right? 5 we've sorted, and 6 you can't divide. Okay, so in fact, of all the sort of possibilities, all right, and I'm going red dice, blue dice, green dice, right? We could get a 5, and then remember we take the value on the blue and divide by the value on the green. In order to get a common ratio of a half, we could have a 1 on the blue and a 2 on the green. We could have a 2 on the blue and a 4 on the green. We could have a 2 on the blue, sorry, a 3 on the blue and a 6 on the green. Right, those are the only ways you're going to get a common ratio of a half. All right, then to get a 2, all right, we need our common ratio to be 4/5, and the only way that's possible is to get a 4 on the blue and a 5 on the green. All right, and a 4, we need a common ratio of 3/5, and the only way that's possible is to get a 4 on the red, 3 on the blue, and a 5 on the green. Right. So in fact, there are 1, 2, 3, 4, 5. I think there might be one other one that I'm missing. Yeah, I'm kind of worried that I'm missing one, but at the moment I'm getting 5 out of 216. Okay, I'm just going to pause and check my thinking on that. Yeah, indeed, there are in fact 6, and the reason there's 6 is that we can get a 6 divided by 3/5. All right, because the 6 divided by 3/5 would also give us 10. All right, and sorry, 3/5, which would mean we need a common ratio of 2/5. So if we got a 6 on the red dice, a 2, and then a 5, all right, so a total of 1, 2, 3, 4, 5, 6 out of 216. Okay, so quite a fiddly question, Yeah, and it caused a lot of debate as well. Right, I think, yeah, that was from last year's paper, so that's all of them.